So this is going to be our approach 1. And this is drawn here on this 3D mesh plot where that green surface is the gradient at the minimum. And what we see is that's where the gradient is equal to 0. And that red dot is the optimal point that we're going to be looking at. Okay, so let's go ahead, take this gradient, set it equal to 0, solve for W0 and W1. Those are going to be our estimates of our 2 parameters of our model that define our fitted line. Remember, that's our goal. Okay, so I'm going to take the top line and I'm going to do a little bit of algebra. I'm going to do it quickly, and I'm going to assume that you, if you would like to, can go through and verify that what I did is correct. But I'm going to take the first line and I'm going to set it equal to 0. The top line, when you set it equal to 0, results in W hat 0 is equal to the sum of yi over n minus W1 hat sum of xi over n. And these sums go from I equals 1 to n, just as they did here. And the reason I'm putting the hats on are now, these are our solutions. These are our estimated values of these parameters. And what we see is that our estimate of the intercept for our regression line, well, it takes, what is this? This is our average house sales price but we're not simply going to set W0 equal to the average house sales price. We're going to subtract off our estimate of the slope of the line. That's W hat 1. And what is this term here? That's multiplying W hat 1. Well, this is our average square feet of any house in our training data set. Okay, so there's a nice intuitive structure to our estimate for W hat 0. But again, this is in terms of W hat 1, so we have to provide another equation to actually get at a solution. And so if we look at the bottom line of this gradient, the bottom term of this vector, shouldn't call it line, I guess I'll call it the top term of the gradient, and this is the bottom term of the gradient. If we solve, set it equal to 0, we're going to get sum of yi xi minus w hat sum xi minus this should be w0 hat, w1 hat sum xi squared equals to 0. And now what I'm going to do is I'm going to take W0 hat, my equation for it, and I'm going to plug it in. And so what I end up getting out is that W1 hat, once I plug W0 hat in terms of W1 and solve for W1 hat, I get W1 hat is equal to the sum of yi xi minus sum yi sum xi over n divided by sum xi squared minus sum xi sum of xi divided by n. Okay. Anyway, the point is that it has a closed form, pretty straightforward to go and compute what this is. And what we see, I want to note that what we have to compute W hat 1 and then plug that in and compute W hat 0 is we need to compute just a couple terms. We need to compute sum over all of our observations yi. We need to compute our outputs yi, sum over all of our inputs xi, and then a few other terms that are multipliers of this. Or of our input and output. So we need to compute just 4 different terms, plug them into these equations, and we get out what our W hat 0 and W hat 1 is. The optimal values that are minimizing our residual sum of squares. The take-home message here is that one way we can solve this optimization problem of minimizing residual sum of squares, take the gradient, set it equal to 0, and this is the result.